There we go.
Any questions?
I will take that as a no. With us, Louise? You're not? Sorry.
It's okay, forgive you.
There's testimony. This is what's written down right there.
Dr. Fox, what is HA?
What is HA?
Yeah.
Whoever was it?
I do not remember what HA stands for. It's a mystery. All right, picking up where we last left off. We never finished this problem, I believe. The resistors. A, B, C, D, E. And we reduce this down to that was 1.2 ohms for that combination. And then brought in, so the resistance of DC combination was 1.2 ohms. The resistance of BCD was 5.2 ohms. And the resistance of BCDE was 2.5490 ohms. That's what I have written down. Does it match what you have? Right, so that. that's 6 ohms, 7 ohms, and 2.549 ohms, 1 ohm, 20 volts. That I believe is as far as we got, at least that's as far as my notes went. Okay. Ultimately, we're trying to find what is the current flowing across each battery, or try that one again. What is the current flowing across each resistor? And in terms of creating a, yeah, okay, I found the equivalent resistance of this right here. But how do I then combine them? Well, I know that my current comes in here, and this is just one giant junction right there. Because I have nothing in between any of that stuff, they're all connected, it's just drawn strangely. So I have a junction here, I have a junction here. This junction is connected to the 7 ohms. This junction is connected to the 6 ohms. Or I guess that is connected to the 6. This has the 7 over here, so that junction right there is this junction right here, this long, elongated one. That is basically here. So in between, and this one right here is this one right here. So in between these two, I've got my 7. In between these two, I've got my 6. And in between these two, I've got my 2.549. Just taking a quick moment to make sure that there's not a careless error there. Yeah, because anything that flows through that structure has to flow through the 6. Okay. Yep, I'm comfortable with it. Now what? Still trying to find that total equivalent resistance.
You put the 2.5 ohms and the 6 ohms in series.
Yes. Okay. Resistors in series are that's the simple one, like capacitors in parallel. 1 ohm. I got 7 ohms going down this path, and my total resistance here is 8.549 ohms. Now what?
Now the 7 and 8 are in parallel.
All right. Now, if they're both 7 ohms, right, they're not, but if they were, then my equivalent resistance would be 7/2, 3.5. So I know that the equivalent resistance, since this is a little bit more than that, it's going to be something a little bit more than 3.5 ohms. Let's find out. So this is resistor. This is B, C, D, E, F. And this is G. So 1/7 plus 1/8.5490 equals 1 over the equivalent resistance of basically B through G. And what is that? Word around. 3.817. What is it?
That's 3.849.
849. And we are now at and our last equivalent resistance. What do we do now?
$4.849.
What kind of voodoo math was that? All right, they are indeed in series, and you would just add them straight up. 4.8490. Oh, we were going out to 4 decimal places. So what was?
8487.
8487. All right. So at this point, we can figure out the current flowing out of the power supply. And how does one do that?
Ohm's law. Ohm's law.
Yep. What is Ohm's law, by the way?
Voltage equals current times resistance.
Yeah. So voltage is the current times the resistance. And so we have 20 is equal to I times 4.8487. So what is the current flowing out of the power supply?
.1248 amperes.
4.1218. 48
Yes, sir.
amperes. All right, well, we finally got our current. I know I have .1248 amperes. So what is, do we know current flowing across any other resistor? Or any resistor, since other implies we've gotten one.
F.
Say it again?
F.
We have the current flowing across F.
Wouldn't it be the same?
All right, you have to go louder.
Wouldn't it be the same? 4.1248.
The same here? Well, there's a junction there. Whenever there's a junction, there's a split, so you can assume that the current is not necessarily the same. I mean, there is a situation, there are some situations where you can get away with that, but not unique. A requirement, one requirement would be symmetry. But do not assume. The junction's gonna split up current. So I know it's going down the power supply. Is it gonna go across any resistors that where the current is not gonna split before it?
A.
Yeah. So it's gonna come across here, whatever's coming out of the power supply has to flow across A. And I want more room here. So I'm just gonna make this bigger. A, B, C, D, E, F, G. One phone, two, 4 phones, 5 phones, 6 phones, 7 phones. So I have a current flowing across here of 4.1248 amperes. Now, shortly after that, we hit that big junction. Now, when solving a problem like this, we're going to be flipping back and forth between finding potential drops and finding current. So I know the current flowing across that 1 ohm resistor. What is the potential drop across it? What's the voltage across resistor A? Or how would you find it?
Resistance times current,
Yeah.
so it'd be 4.1248.
So as I'm going across it, minus 4.1248 volts. And let's see if I can keep consistent with the color scheme. Now I want to see if I can figure out a path. It'd be really nice if I could get a path here where the current, I can have a voltage loop with only one unknown resistor, or one resistor where I don't know the voltage. What's the simplest path? The one that crosses the fewest number of resistors. And I'm talking a path, a voltage loop, where I start at some point, I go around, I come back to where I started.
Going through G.
Yeah. So if I start here, go across the battery from negative to positive, so I gain potential. Going along, go across here, I'm gonna lose 4.128, come across G, so I have to lose the rest of it because I'm back at 0 again. So how much do I lose going across here? Across this. So if I gain 20, lose 4 point something, and then lose another 20, I'm end up at a negative potential when I get back to where I started.
15.8752 volts minus.
0.8752.
Yeah.
All right, so now I gain 20, I'm gonna lose 4.1248, I'm gonna lose 15.8752, I'm back at 0 again. Which is what I want. Because we are assuming that Kirchhoff is correct. So now that I know the voltage drop across the 7 ohm resistor, what is the current flowing across that? What is the current flowing across resistor G?
Two point 2679 amp.
How'd you get that?
15 the voltage divided by resistance.
Alright, it's 2 point what?
2679.
2.2679
Yeah.
amperes. We're cooking here. Alright, so I know, so we just did a voltage loop, so probably we're gonna be doing a junction rule. In other words, current flowing in equals current flowing out. So what is the current flowing across? Well, if you think about what are the junctions involved here. We have a junction here, a junction here. We have many junctions, actually, that's all one big junction right there. Those are the junctions. That's the place where current can split or join back up again. So looking at the current flow in and out of this junction right here does not really work particularly well at this point, because I have 3 different branches the current is going to be splitting along, so that's not simple. Is there a junction, and we can actually label this.